This recording is for Primary Math 5. It's the challenging word problems on pages 3 through 5. The challenging word problem book, page 3 through 5. The first problem, Mr. Lee is giving stickers away, and the kids are all sitting in a circle. And he has 100 stickers to give away. The question is, if he moves around the circle in that order, who's going to get the last sticker? All right, well, certainly you could count to 100, and you could hand them all out like that. You could think about it like a math problem, though, by trying to figure out when do you run out of the ability to give everybody a sticker, and what is the remainder? In a sense, you're thinking 100 stickers divided by the 6 children, and another, again, because we're working on Singapore math, let's think in terms of mental math as much as possible. 100 could be considered 60 and 40, and the reason I did that is because 60 is a multiple of 6. I want to take these all down to multiples of 6 because what that tells me is how many I have left over. You see, this is 10 groups of 6. 36 is 4 groups of 6. So what happens is we have 14 stickers being handed out to everybody, but when we're finished handing them out to everybody, I have 4 stickers left. So 1, 2, 3, 4. The last sticker is going to go to Jenny. Now notice on the instructions, the word problems will always tell you to answer the questions, show your work, and write your statements clearly. So the fact that Jenny gets the last sticker needs to be stated, and preferably put a box around your answer, big enough that your answer doesn't get lost in the sides of the box. Number 2. This problem is going to take some sort of a chart to help us figure out how to solve it. What we have is that a 2-digit number is 3 times the sum of its digits. So we're talking about a lot of moving parts, really. There's a number, and there's a sum of its digits, and there's a 3 times the sum of that digits. And of course, the number is a 2-digit number. We have to start with that assumption. Now, if you can read this and before you start, pause a minute and kind of digest it a little bit, here's an interesting thing. This 2-digit number is 3 times something. That tells me that it is a multiple of 3. So when we're starting something, a lot of times you look at this and you think, you know, there's a bunch of 2-digit numbers, right? And so I can't try all of them. How am I going to limit this down? One way is to realize that I have a 2-digit number and it's going to be a multiple of 3. So like, for example, I could start with the number 12. The sum of the digits is 3. 1 plus 2 is 3. And 3 times that number is 9. And the question that we're asked is, we want to find a 2-digit number that is 3 times the sum of its digits. I want to know when are the 2 outside columns the same. I want this number and this number to be the same thing. Well, that one certainly wasn't. But also I know this number is a multiple of 3. 15, 1 plus 5 is 6. That's not even a 2-digit number. So far we're doing fine, or at least we don't have an answer. We're doing fine that we haven't found one yet. 1 plus 8 is 9. Sorry, hold on one second. I did that wrong. This is supposed to be 3 times the sum. The sum is 6. 3 times that is 18, but 15 is not the same thing as 18. 18 has a sum of 1 plus 8 is 9. 3 times that is 27. That's not the right number either. The number is 21. The sum of the digits, 3 times the sum of the digits. I want the number and 3 times the sum to be the same. Now, maybe you're noticing already, along with me, I have a pattern going here. 9, 18, 27, 9, 18. I bet the next number is 27, and guess what? 27 is the next number on this side too. 2 plus 7 is 9. 9 times 3 is 27. We have now found what we were looking for. A 2-digit number, 27, is 3 times the sum of its digits. And we have just checked our work and found that indeed 27 is that number. When the hint is guess and check, what we want to do is find some sort of a organized way to find that. And in this case, it was especially helpful, well, it's helpful to have a chart, but it was especially helpful to be able to take the number of possible answers way down to realizing it has to be a multiple of 3. And so then my guess and check took a lot less than if I started with the number, say, 10 and went all the way up to 27 from there. Number 3, Lewis wants to arrange his CD collection in stacks of equal size. He arranges them in stacks of 2 and 3 and 5, and each time he does, he has 1 left over. Now, I've just given you a big hint, right? We're talking about a remainder theory again, and our remainder, kind of like a number 1 when we're talking about the 100 stickers, the remainder is going to be 1. Now, think with me a minute. If you have a remainder of 1, then basically you're going to take a multiple and add 1 to it. 3, if I divide it by 2, has a remainder of 1. If I had 5 CDs and I put them in stacks of 2, I would have 1 left over. And 7 and 9, same thing. To have a remainder of 1 means you're going to start with a multiple and you're going to add 1 to it. And that will be a number that gives you a remainder of 1. So what we're really asking is to find the common multiple, the least common multiple of 2 and 3 and 5, and then we're going to add 1 to that least common multiple. So, do you remember how to find least common multiple? Since 2 and 3 and 5 are all prime numbers, actually all we're going to do is multiply them together and come up with 30. So 31 is the number of CDs that he had. Now, let's check that and make sure that we're understanding multiples correctly. If I have 31 CDs and I put them into 2 stacks, or into piles of 2, I will have 15 stacks and 1 CD left over. If I have 31 CDs and I put them in stacks of 3, then I'm going to have 10 of those kind of stacks, and I'll have 1 left over. If I have 31 CDs and I put them in stacks of 5, that will be 10 stacks of 5 CDs each, and I have 1 left over. Now notice the question says, what is the least possible number of CDs you could have? Why does it say that? Well, 31 CDs works, but the next common multiple, it's not the least common multiple, but the next one would be 60, and so 61 CDs would work, and 91 CDs would work. All of that would work as well. But if I want the least number, the smallest number that he could have in his collection, then it would be 31 CDs in that collection. Number 4. Pages of a book are numbered from 1 to 100. We're trying to find how many pages contain the digit 2 but are not divisible by 2. We have 2 criteria to meet, and we have to do both of those. Now, when I read this, this phrase stands out to me as something very important. There's another phrase, another word we have for that that you may or may not have jumping up in your head right now. Think about this a minute. If something is divisible by 2, if it's divisible by 2, it means 2 goes into it without a remainder. We call that an even number. And we want to find one that is not even, because it's not divisible by 2, so we call that an odd number. So really, they made it complicated. What we want to know are all the numbers between 1 and 100 that contain the digit 2 and are odd numbers. Now, that really narrows it down, right? Because the digit 2 would either be in the ones place or it would be in the tens place. If a digit 2 is in the ones place, those are all even. So what we're saying here is there are no 2's in the ones place. And in fact, if it's going to be an odd number, then the 20's don't all work either. 21 is an odd number, and so is 23 and 25. 27 and 29, those are all odd numbers that have a digit 2 in them. The other 20's are even numbers. They're divisible by 2, so they don't work. The question is, how many numbers contain the 2, a digit 2, but are not divisible by 2? And the answer is, there are 5 numbers that do that. Notice that the question was not to name the numbers. We found them, we could name them, but when you're answering the question, make sure you answer the question that was asked. There are 5 numbers that have a 2 that are not divisible by 2. Number 5, there's a jigsaw puzzle with 50 pieces, and when you join pieces together, it's considered a move, and they want you to find the least number of moves needed to join all 50 pieces. The hint is a great one. Simplify the problem. Consider a jigsaw puzzle with fewer pieces and look for the pattern. All right, well, let's start with a jigsaw puzzle with 5 pieces. Now, for simplicity, I'm going to call my puzzle pieces A, B, C, D, E, and E. One move would be to put A and B together, and I could put C and D together. Then I could link AB with CD, and then I could take piece ABCD and link it with E. Now I have all of my puzzle together, and I've done that in 4 moves. Well, a 5-piece puzzle in 4 moves, it seems like we ought to be able to do it faster than that. We could try another way and say, well, what if we put A with B, and then we put A and B with C, and then A, B, and C with D, and A, B, C, and D with E. Well, that's another way to work it, but I also have 4 steps to solve it. Now, this is one of the reasons this class is for the adults and not the students, because I can tell you that, and with your adult abstract mind, that makes sense. You might need to take out something concrete to show your children. Instead of the letters A, B, C, D, take out 5 objects, and you don't have to, they don't even have to be puzzle pieces. You can just say, you know, A and B are now joined, stack them on top of each other, use plates, whatever. How long until they're joined together? And you can find out that you can do it 5 plates or 5 whatevers require 4 moves to be joined together. Now, one problem is not enough to make an entire decision based on, and since I used an odd number this time, I think I'm going to try it again, and this time I want to use an even number. So if I pick an 8-piece puzzle, A, B, C, D, and E, F, G, H are my puzzle pieces, and I want to see how much it takes to join them together. A joins with B, and C with D. When I'm just doing a lot of writing, there's no reason to leave the recording running, and this way you don't have to watch me write it all down. But I've done all of the joining. You can pause the recording and look at it as long as you want to, and you can see that it took me 7 moves. 8-piece puzzle required 7 moves to join them. Based on the fact that I've done a couple of examples and I've got a pattern here, and based on the fact that I've done an even and an odd to make sure, I feel pretty confident at this point making the statement that a 50-piece puzzle needs 49 moves to solve it. It seems like that shouldn't be true, but it is. Number 6, Jill is throwing darts and she scores 100 points total. One question they want us to answer is how many darts were thrown? And the next question we want to answer is, where do they land? In other words, what are the ways that you can take those numbers, 12, 19, 23, and 30, and come up with 100 points? Now, this problem doesn't say find the least amount of darts you have to throw or the most amount of darts you have to throw. You're just supposed to find one of them. Look for any group of numbers that have a sum of 100. There are more than one option, and I'm going to show you all of them that I have found. I believe I found them all, but I will show you what I found. The key here in my mind is that you have to make tens. So think in terms of, if I have a 19, I need a 1 to go with it. I don't have a 1 to go with it. I do have a 12, and I could use that 12 and put one of them there and one of them here, and that would make tens. When I do that, that would give me 20 and 40, and one more is 50, and that looks very positive, because if I do it again with another 19 and another 19 and another 12, and I have another 50, then that would be 100 points. And I did that with 6 dice, and I did that with 4 19-point dice and 2 12-point dice. So that is one solution to the problem. Another thing I noticed is that 12 and 23 make a 5. So if I do that twice, I have a 10. So again, counting in tens, I have 10, 20, 30, 40, 50, 60. All of my ones make another one, so that gives me a total of 70. And very excited to notice there is a 30-point spot on the board. So if all of these make 70 and I add a 30, then that gives me another way to make 100 points. That required 6 dice. I guess I should say 6 die. No, it's actually darts. I'm not thinking the right thing at all. Don't see many dice that have that kind of count on them, do we? Let me fix it real quick. Okay, so these 6 darts that we're using, I have 2 with 12 points. I have 2 with 23 points. And 1 with 30 points. And I'm really going to get fired today because now I realize I actually used 5 darts to make that. All right, and I found another way to do it. It occurs to me as well that if I use 23 3 times and 19 once and 12 once, look at my ones. I have 3, 6, 9 ones, and have another 9, and so the 2 ones here can go respectively to all of those and make into tens, an even 10. So these are 60, with another 10 make 70. This one becomes a 20 when I add that other 1 to it, and this is a 10. Once again, 70 and 20 and 10 make 100. So on this one, see if I can get it right the first time here, I have 5 darts. I have 3 that are 23-point, one 19-point and one 12-point dart. So any of those three solutions will work just fine. There may be others, I don't think so. Haven't found them myself. Always makes me stop and think. Any of those answers works just fine. Number 7 talks about 6 tennis players joining a tournament, and everybody's playing against each other one time. I'm going to call my 6 tennis players by very original names. And I'm going to just make a drawing and see what I have to do. The hint talks about simplifying it and doing it with fewer players. Really, 6 is not that many players to do. But what happens is at some point in the tournament, player A plays against player B, C, D, E, and F. Player B has already played player A, and so he only needs to continue playing C, D, E, and F. C, in a similar way, just has to play D, E, and F. D plays players E and F. Once E gets to this point, he only has to play player F, and F has nobody left to play. If I count the number of games played, I come up with 5 plus 4 plus 3 plus 2 plus 1, and that's a total of 15 games to be played in this tennis tournament. When everybody's finished, there have been 15 games played. Number 8. I'm adding up 10 numbers, and the sum, I'm told, is 2,783. Now, if I take one of those numbers and I change it from 397 and I make it into 502, the question is, what is the new sum? Well, the long way would be to take 2,783, subtract the 397, so you have the sum of the first 9 terms, and then add 502. And that would give you the right answer. But it'd be a lot shorter if instead of subtracting 397 and adding 502, if we just found out how much did that number increase. Now again, we want to really work on mental math every chance possible. To go from 397 to 502, first I'm going to go up 3, and that puts me at 400. From 400 to 502, I have to go up 102. All told, I had to increase by 105. If one number increased by 105, then my sum is going to go up by 105. And I can add those numbers together and find out that my new sum is 2,888. Now, if you did it the longer way, you'd come up with the same exact answer, but it's good to begin looking at the numbers and realizing what happens. How does that 397 affect it? What happens if it changes to 502? Well, if that number goes up 105, the overall sum will go up 105, and that's all you have to do. Number 9. We start with toy bag P and toy bag Q, and we find that in the beginning, there are 12 toys in P, and there are 66 toys in Q. And then, very kind Mrs. Murray comes along and gives some toys to both bag P and Q. And when we're finished, change colors one more time, what we have is that bag P and bag Q have a new relationship in that Q is 3 times the number of toys as bag P. So we started with the blue diagram, we moved to the orange diagram, and what happened in the middle was the green box was added. The question is, how many toys did she add to the bag? What I'm trying to figure out is, how big is this? Remember, they're the same, and how big is it? At first, it seems to me that we don't have enough information, but there's a really basic skill that you'll see a lot in the Singapore math books. And and that is to ask yourself, what is static? Static means does not change. And the thing that doesn't change in here, if you start with 12 and 66 and you add the same amount, the difference between the toys is static. By that I mean, in the beginning, Q had 54 more toys than P had. If you add the same amount to both of them, in the end, Q is still going to have 54 more toys than P has. According to the drawing, if there are 2 more boxes and those boxes represent 54 toys, then I know that each box is 27. And keep in mind, all the boxes are the same. So P started with 12 toys and P ended with 27 toys. In the middle of all of that, what had to happen would be that Mrs. Murray must have given 15 toys into bag P. We're told they both got the same, and so we think the answer is 15 more toys. Why do I say we think? Actually, that more toys goes with something else. 15 toys were added is what I need to say. Now, before I finish and walk away from the problem, I'm going to go ahead and check the work because it is so easy to make a mistake. If I start with 12 toys and I add 15 toys, I do have 27 toys at the end. If I start with 66 in the other bag and I add 15, then I end up with 81 toys in the end. The question is 81 3 times as much as 27? And the answer is yes, it is. So that confirms for me that my answer, that there were 15 toys added, is the correct answer.